Welcome to note set number 26. I'm laughing because I just hit record and my dog started barking immediately. uh, so anyway, yeah, I record these at home in the comfort of my bedroom or wherever. And so, yeah, as you've noticed, you occasionally hear my dog in the background. Um, she's barking now because my wife is driving down the driveway as we speak. And so that's what she's barking at. Anyway, note set number 26. Our second of two on FFT algorithm. So in the previous one, we kind of developed it ad hoc, although not that ad hoc, but just kind of the way someone might stumble into it. And so if we think about, how do we get new ideas? How do we develop new methods? This is kind of a good illustration. So, in the previous note set, we kind of played around and decided, oh, splitting things up, reindexing things seemed to get us somewhere. And so in this note set, we would maybe take the next step of somebody developing a new idea who stumbles onto something and says, well, let's try to make this a little bit more systematic and see what we might be able to get out of this. So we won't see everything about FFTs in here, but we'll lay the groundwork, and then if you ever need to go on into more detail, you'll have that groundwork on which to draw. So this is drawn from two sections of Proacus and Monolacus, and off we go. This is called the divide and conquer approach, and we kind of saw that kind of behavior in the previous note set, where we divided into the even indices and the odd indices of our input signal. So that was the dividing part. And now we're going to try to make this a little bit more formalized and generalized. And we'll start this very simply and just say, suppose we have some n that we can write as the product of two integers, L and M. So in other words, we're saying n is not prime, so it can be factored into two integer factors. And obviously, we saw that for our previous example. We had a power of 2, so we could factor it into 2 times 2 times 2 times 2. And so this would be a more generalized approach. N can be factored into L times M. And then, as we'll see, just like we saw in the last one, we would want to extend this idea to more and more stages. So then L and M would each have to be factored into something else. And likewise, as far down as you could go. But they don't have to be powers of 2. But they do have to be factorable to something. And we can always zero pad out to some appropriate number for whatever type of algorithm that we're interested in. Okay, so once we have that, we use the M and the L to kind of set up some alternative mapping. So we're going to map our one-dimensional index, n, into a two-dimensional index, and we could use one or the other of these. So we either jump by M or jump by L. And so we're going to use little l and little m as kind of a 2D index into our input array now. And we'll take a look at what these indexings look like in just a little bit. And simultaneously, we have two options for our output indices. So remember, we're taking n time points and transforming them into n DFT points. So the input signals are originally indexed by little n, and the output DFT coefficients are indexed by little k. So we do the same kind of thing. We map into a 2D index array, which we'll use P and Q to keep track of. So we'll illustrate here with the input mappings. The output mappings are similar. We have a row-wise and column-wise. So for row-wise, if we think about L and M being up here, And we think about marching through those in a way that would get us to go sequentially through little n. We can see that as we go across the top here, we're changing m, so we're getting, if we change m by 1, we're getting a single increment in n. So we can see that the one without the big integer in front is what ends up taking us 1 by 1 by 1. And then, so the idea is that little m is now going to go all the way out to m minus 1, and then we would reset back to 0 and bump L up by 1. So now we're going up to L equal to 1 and back to M equal to 0, and we pick up X of M, and now we march across the little m again, incrementing little m to 1 gets us to m plus 1, and then m plus 2, and so on, all the way out to 2m minus 1, and then we wrap back. So you'll notice that if we go down the columns, let me clear some of this stuff off here, and let me try it this way. It's a little faster. If we go down the columns, we see that we're, as we change L, we're jumping by m. So we're going 0 to m to 2m, 3m, and so on, all the way down to L minus 1, capital L minus 1 m. So remember, m and L, their product is equal to n. And then we get all the way to the end. This very last element is Lm minus 1, so that's n minus 1. That's our last term. So that's rowwise input mapping, and it's called rowwise because we're taking m along the rows, and we are putting in our signal in this direction. And so what we're going to do is we put our signal in that direction, and then we're going to take our DFTs down the columns. So if you think about what we did last time, you could think about going, think about having two columns, and we went 0, 1, 2, 3, 4, 5, 6, 7, and so on. And then so we would have all the even ones in this one. We're thinking of m equal to 2 in this case. We have all the even indexed ones here. We have all the odd indexed ones here. And we took a DFT of the even ones, and we took a DFT of the odd ones. So what we're seeing here is very, very similar. Now, we can also do a column-wise input mapping, and really it's no different. We're just going, it's literally just taking this the other way. The only difference is that we're filling down this row, or down that column, then we come back up to the top here and fill down this way, and so on. So the only difference is that we still have the same size. We have an L by M array. It's just how far we go in each direction is slightly different. Okay, so 2 different ways of doing our input mapping, and there are 2 corresponding ways to do our output mapping. And we've already seen a little bit about how how the mapping coordinates with taking the DFT, and we still haven't proved anything that gets us anywhere, but we're going to see how this machinery actually can be used. So what we're going to do is exploit one possible choice, column-wise input mapping together with row-wise output mapping. So here's what we defined to be those 2 mappings, and here's our standard DFT equation. So we're just simply going to plug those in. So everywhere there's an N, we'll plug in this, and everywhere there's a K, we'll plug in that. And so here's our N mapping, our input mapping. Here's our output mapping on the K. And then here we're really just imagining that our X gets put into the array, so it now has a two-dimensional arrangement. There's no reason to put in the explicit form for N there, because we're just saying we're keeping track of where our X values are. Okay, so given that, let me get rid of all that. So given that, we need to focus on what's going on here with our W factor. So what we do is we FOIL this out, so we get an MP times L is our first. And we're going to get 4 terms. So we'll have W raised to the sum of 4 things, and then using properties of exponentials, we can write that as the product of 4 different terms. So we'll have MP times little l, so that ends up over here. That's the first. We'll have the outsides. Let me clear this off here. We'll have the outsides, which will be MP times ML, and that's there. We'll have the insides, which will be QL, that's there. And then we'll have the last, which will be Q times ML, and that's there. So we've got all terms accounted for, so that's good. Good to keep track of all that as we develop things. All right, and so now what we're going to do is kind of look at what each of these things does. So we look at this and we say, all right, W sub n, remembering that ML is n, we can rewrite it this way. So we've got W sub n to the n, and remember the n in the subscript there means 2 pi over n up in the exponent. So we're going to have a 2 pi over n, and then we end up multiplying that by n. So we end up with a 2 pi there. That's key. And then the 2 pi gets multiplied by an integer MP. So this quantity here is just e to the j 2 pi times an integer. And so on our complex plane, that's always right there. Some integer multiple of 2 pi always brings us back to right there. So we know that that number is equal to 1, so we can replace that by 1. So this effectively is gone. Then we look at these two, and we use the same trick that we saw before when we had a 2 up here and we ended up bringing it down here for an n over 2. Well, we can bring the L down and have an n over L. And we can bring the m down and have n over m. And remember, since n is m times L, this is really W sub m, and this is really W sub L. Okay, so, and then the last term, we don't do anything to it at all, because there's really nothing to do. It's in standard form already. It's just W sub n raised to the LQ. All right, so we replace this quantity here. Remember, that's gone because it's 1 by these 3 things, and those 3 things are showing up inside a summation over m with a summation over L. And so what we can do is anything that doesn't depend, and we can interchange the order of those. Oops, I just noticed that I have an error here. That should be m minus 1, and this should be L minus 1. Interesting fluctuation on the copy and paste error there. Anyway, we can reorder the sum. We can pull things out in front that don't depend upon a certain sum. So if we put the m sum inside, we have this here that does not depend on m, so we can pull that out in front. We also have this that doesn't depend on M, and we could pull that out in front as well, but I choose to pull it out to the right. So we've pulled the two things that depend only on L, one to the left and one to the right, leaving this thing in here where we've left just this term. That's the only one that depends explicitly on M, so it has to stay inside that sum. The others relative to M are constant, so they would be the same number in every term, so we can pull them out in front. Okay, so that's what we're going to do, and then we're going to look to see what it is that we've accomplished in doing that. So let me put that back. I have an L minus 1 there. So if we look at what we're doing here, we've got a structure here for an N over L DFT, right? So N over L is actually M, so we can replace that by M. So this structure is an M point DFT structure, and we're doing it over M, and so we're computing the M point DFT of the rows. We used a column-wise input mapping, so we're doing our input or our DFT over the rows. Remember, L was down, M was across. Okay, so and we'll call that quantity f of LQ, right? Because obviously it depends on L, so for every fixed L we'll do this. So we'll have to do this sum essentially for each value of L, and it also depends upon Q, so we would have to do this for each value of Q. So we can compute that in principle. So we would get this array of numbers, and then what are we doing? So then to that we apply this thing for every LQ pair. We apply this complex number. So to each element of this, it gets multiplied by one of these twiddle factors. We've seen that before. And then we take that thing and view it as a function of L. So for each fixed Q, so now down the columns, we're going to take a DFT. And this is the proper W form for an L point DFT. N over M is L, so we're all properly set up. So we're doing an L point DFT down the columns. And so all of that computation gives us all of the correct DFT points, just indexed differently. So indexed in a column form, or in an array form rather than as a vector. So let's go on to the next slide here and take a look. So suppose we have n equal to 15, and we factor that 15 into 3 times 5, and so we can rearrange our input this way. So we can see that we've done column indexing, 0 through 4, 5 through 9, 10 through 14. So there's our column indexing. So then we're going to do DFTs, 3-point DFTs, across each row. So here are those DFTs. So that DFT will take x0, x5, and x10 as inputs. The next one down would take x1, x6, x11 as inputs. And so on, and so on, and so on. And so we'll now get an array that's the same shape as this. So it's 3 by 3 across, 5 down, and we apply this array of twiddle factors to that. And so we literally just count that way. So the L and the Q index this. So remember, the we've done our DFT across this, so across the row, so the letter that we use to index this gets changed over here to Q. So Q is now indexing across here, L is indexing down this way. So we would index our W sub 15 LQ, that's what our twiddle factors are. So we apply 15 twiddle factors, some of which will be effectively negligible. There'll be ones or some simple things like that. And then after we apply that, our rule says from our development to take 5-point DFTs down the column. So the numbers that come out of this twiddle factor multiplication, we would do a 5-point DFT, a 5-point DFT, and a 5-point DFT, and we end up with a 3x5 array of our DFT results. And so we would get as indices now, we would get x of 0, 1, 2, x of 3 over to x of 5, 6 over to 8, 9 over to 11, 12 over 14. So we would index those out across the rows. And so, my comment here is it looks like we've made things exceedingly more complicated. But as we saw in the last set of notes, we're really just splitting things up into ways that we can then take advantage. So there's a lot more to happen to make this work effectively and efficiently. Remember, we played with the structure of the twiddle factors when we did the development in the last one, so there's going to be some advantage there. And also, we played around with the structure inside a 2-point DFT, so there may be some things that we can do inside here as well. And so this is just the tool by which you can explore a lot of different possibilities. And like I said, I'm only trying to present to you the basic ideas here, not give you a complete introduction to all types of FFTs. I couldn't do that because I'm not well versed in that area. It's not something that I've worked a lot in. And B, there are entire books, really thick books, on all the different ins and outs of FFT algorithms. So this will at least give you an idea of what underlies all of those. All right, look at the next slide. And just to see, to link this back to what we did in the previous set of notes, let's use this viewpoint to develop our Radix-2 decimation in time algorithm. So, so there we started off with n equal to a power of 2 to the v, and to apply the ideas that we're talking about here, the divide and conquer approach, we'll let L be equal to 2 and M be equal to N over 2. And so then if we do our column-wise input mapping, we will go 0, 1, 2, 3, 4, 5, 6, 7, and so on and so on and so on. So that was our mechanism for filling in a column-wise manner. And remember, when we fill in the column-wise manner, we then take the DFTs across the rows. And so we can now see that we are indeed getting exactly what we saw last time. We're taking a DFT, n over 2 point DFT of all the evens, all the even indexed samples, and we're taking an n over 2 point DFT of all the odd indexed samples. Okay, so that's good. And then visualizing it like we've seen on the previous page, here's our input array, indexed column-wise. And so then we're applying our n over 2 point DFT across each row. So here's one of our n over 2 point DFTs, and then right below it is a second one. And then we apply the twiddle factors. And if you remember, the twiddle factors were either 1 or on one side of the butterfly structure, and were WN to the K. So we only show them on the bottom part of this, not on the top. So the even indexed ones coming out of the DFT didn't get hit with a non-unity twiddle factor. Okay, and then the last thing we saw was that the combination of those gives us, or to combine those results, we used 2-point DFT. And if you look at how, compare how we're showing it here to what we saw in the last notes, you'll see that this is exactly what we did before. But in this viewpoint, we're now doing DFTs, 2-point DFTs down the column. And so the idea is that we've applied this divide and conquer structure once, and now we're going to apply the divide and conquer structure to each of these n over 2 point DFTs. So we'd apply it to that one, and we'd apply it to that one. That's the same thing that we saw in the last set of notes, where we went from to extended to stage to stage to stage. So we started off with 8-point in our example, and we saw that we got 2 4-point DFTs, which were then combined with effectively 2-point DFTs with twiddle factors. And then we broke down those 4-point DFTs into 2 2-point DFTs for each of them. So that's this idea right here. Okay, so great. That's what we're talking about here so far. And so now we can develop the other Radix-2 FFT algorithm. So it's the same scenario. We've got a power of 2, but now we're going to switch. We're going to put m equal to 2 and L equal to n over 2. We'll still use column-wise input mapping, but now our columns are long. They're n over 2 long, and we're going to do row-wise DFTs. So we'll start off doing 2-point DFTs right away, rather than what we just saw. So if we visualize this this way, here's our input array put in here, and across the rows we're doing our 2-point DFTs, and then we apply our twiddle factors. And if you look into the structure of the twiddle factors, you'll find that for this structure you only have to put them down this left side, not down this right side coming out of here. And then the resulting combination, well, our divide and conquer says the next thing that we do is the other size DFT down the columns. So we would do n over 2-point DFTs down the columns. And when we're all done, we get our output array indexed row-wise. So 0, 1, 2, 3, 4, 5, and so on and so on. And then we would take each one of these n over 2-point DFTs, and we would apply the same kind of mapping to those. So we would map the output of each of these. So all of these things, let's say for example, all the things here, let me finish up there. So we would take these and we would re-index those using this scheme again. Take 2-point DFTs across the rows of that re-indexed array, and then apply twiddle factors and take n over 4 point DFTs now down the columns of that, and so on and so on and so on. And since we have a power of 2, we could repeat this process for a total of v times v stages, just like we saw before. But because this is starting the other way, and notice that we're not applying DFTs to even and odds at the beginning like we did before. We're actually applying DFTs across a much bigger straddle, so to speak. This is called decimation in frequency, and the reason is that when we get all the way to the end, we'll see that this is kind of the reverse structure that we saw for what's called decimation in time. So let's go to the slide where we apply this idea to an 8-point decimation in frequency. And so you can see when we apply this first one, you can see that we get that evens and odds split on the output side. Whereas the decimation in time started by splitting the input into even and odd. So we could actually derive this in an ad hoc way by saying, all right, let's think about computing only the even indexed outputs and figure out what that looks like. And then what do we have to do to compute only the odd indexed outputs? And we would recognize that that leads to a 4-point DFT with some butterfly structures strung in front of it. And then we would continue applying that idea. And so that's why it's called the decimation in frequency, because it starts with looking at evens and odds in on the frequency side of the FFT box. And then we would continue this and get 3 stages, because 8 is equal to 2 to the 3, so we would have 3 stages. And if we worked everything out just like we had done in the last set of notes, we'd get something that looks like this. And you'll notice the distinction here, but be careful, it's not just about the ordering of the inputs. It's about how the algorithm was designed that makes the distinction between decimation in frequency and decimation in time. But following this the way that we have so far, we see that we have the input array in order and the output array is in bit reversed order. So this is in some sense the dual of what we just derived in the last set of notes for decimation in time. And if you look at this, you'll see that the butterfly structure is a little bit different for decimation in frequency versus decimation in time. So this is the structure that we had before for decimation in time, and this is the structure down here that we have for the decimation in frequency. So the key difference is which side of the butterfly the twiddle factor lives on. So the difference here is that you apply it first to one of the inputs and then you do a subtraction. Whereas for the decimation and frequency structure, you do a subtraction first, then you apply the twiddle factor. So either one ends up implementing the FFT, and there's some troughs between these things. But really, there's not an awful lot of difference fundamentally between them. If you dig into this in more detail, you can get books and books and books and articles and articles and articles on this that will tell you the finer points of when you want to use one versus the other. But here's some diagrams, and I borrowed these from a book called Understanding Digital Signal Processing by Rick Lyon. This is a very popular book among practitioners, not all that popular among academics, and I can see the reason for that. I like the book, but there are some aspects of it that are a little bit missing. It tends not to deal too much with DTFTs. In fact, it might not even talk about them at all, if I remember right. And so in my mind, it's really hard to talk about the theory of signal processing without really getting into the DTFT viewpoint. I mean, you can see how I use that to envision the connection between CTFT, DTFT, and DFT. But nonetheless, there's some real beautiful stuff in this book, and it's a real no-nonsense, here's how it's done kind of book. So if you find yourself working in an area where you're doing a lot of DSP, you ought to pick this book up and you know, at least recognize that it's coming from a more practical point of view. Armed with that, together with, you know, something like the textbook for this course, will really allow you to really understand how all this is done. Anyway, the point that I'm trying to make with these diagrams is this is for decimation in time, FFT, and we can reconfigure these things kind of by shuffling around the connections. So if you just kind of imagine that these are all connected to each other, but the lines are you know, stretchable, not bendable, but stretchable to some extent. We can move things around, and you can actually take this form that we originally derived, which starts off with the bit reversed inputs over here, and the in order outputs. We can reconfigure that so that we actually have in order inputs and bit reversed outputs. Now, this is not converting it into decimation and frequency. All we're doing is kind of stretching and maneuvering and letting the lines go where they may. We're not changing the fundamental computational structure. And then we can also continue to move things around until we get to a point where we have in order input structure and in order output structure. And so someone might decide that, well, you know, I don't like having to do this extra step of bit reversal, whether it's on the input or on the output. I want to try to reconfigure this in a way that lets me have in order or normal order on both sides. And what is the price to pay for that? Well, here's the deal. If we look at this, you can see that once we've computed two of these things, you know, if we take x0 and x4, we talked about in place. The only place those things are going to impact are those two numbers. So once I compute these two numbers, I'm free to store them back in this place. And likewise, you can track where everything is actually ending up being used. And so this can be done in place. Even if we reorder it this way, this can be done in place. But if we reorder it so that we have normal order on both sides, we can't do it in place any longer. And so here's the issue. Suppose I want to take these two numbers and use them to compute what I need on the next stage. So if you follow the arrows here, and let me try to get rid of some of this stuff here to just see this a little bit better. So if we follow the arrows here, we can see that this number goes here and it goes here. Those are the only two places that it goes. And this number goes here and it goes there. So we take those two numbers and we compute the two results that come from them. That would be this one and this one. Now, to store it in place, we have to put this back in on that memory array, because we don't have two separate memory arrays. We have all the data stored here. We take these two numbers, we compute two numbers, and then let me clear this out here. we compute the two numbers at the far right that are circled in red or ellipticaled in red, and we need to store them someplace. So this one can be stored right back in that place. This one, if we store it in place, we just wrote over something that we didn't use yet. And so you might say, well, all right, maybe that's the wrong order to do it. But you can actually figure out that no matter how you try to order that, you're going to end up writing over something that you haven't used yet. So we cannot have the normal input order, normal output order, and do it in place. So if we want both, we can do it. We'll just need an auxiliary memory location, an auxiliary memory array. So we would need twice the memory. So these are the things that people who spend their days doing these FFT implementations, these are the things that they worry about. And I'll tell you, I've not been that guy. My experience working in industry for 8 years was I figured out the math of the algorithms, and then somebody else was responsible for figuring out how to fit them onto the processors. But there are people who that's their job, and the guys that I worked with, they knew all this stuff inside and out. So I would tell them, here's what my algorithm needs to do, and they would sit down and figure out, well, all right, here's the type of FFTs that we should use, and we're trying to do this in an FPGA, and blah 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 blah. So you can go either way. If that's what you like, you'll go one way. If you don't like it, you'll go a different way. All right, so the key thing is that we either have to do bit reversal, or we have to do extra memory. So those are the prices that we have to pay, and those are trade-offs that one take into account. And just to show you that this is not the case just for decimation in time, here is the decimation in frequency algorithm. Laid out the normal way with normal order at the input. Okay, decimation and frequency with bit reversed inputs. This is the way that we just developed it over here. Decimation and frequency with bit reversed outputs. Both of those can be done in place. And but if we try to get normal order on both sides, we're going to end up needing to rewrite this there, and I haven't used that yet. So same issue, decimation in time, decimation in frequency, both end up with the same thing. Whoops, I don't know what I just did there. I think I added accidentally an extra slide. Yes, so sorry about that. I added a blank slide there in the middle. So we'll finish this set of notes up with just a couple slides on some general implementation issues for FFTs. So we explicitly looked at Radix-2 methods, but we alluded to this generalized divide and conquer approach, which allows us to use any other kind of radix that we want. So by radix we mean the when we say Radix-2, we wanted our n to be a power of 2. So for Radix-2, we have n is equal to 2 to the v. For Radix-4, we would have n is equal to 4 to the v. Obviously a different v if we're trying to keep n the same. For Radix-8, we have 8 to the v. And we could even have a split radix. So we could have a 2 to the p times 4 to the q is equal to n. So those are all different methods that that can be done using this divide and conquer method. So this table over here, which well, it says extracted from Duhamel from 1986, but I actually got this right out of the textbook, so I don't know what it's table 8.2 from the textbook. This is just showing the number of non-trivial real multiplications and additions to compute an endpoint complex DFT. So non-trivial means that some of the multiplications that you might have to do might be like multiplication by 1 or multiplication by -1, and so those aren't actually counted. So you can see some of the trade-offs here, and if say we're looking at an n of 256, if we do Radix-2, we have 1,800 real multiplications. If we do Radix-4, we can get down to 1,392, and if we do a split Radix with 2 and 4, we can get down even lower, and you can see that the additions actually follow that as well. And so pretty much across the board for all these different values of n, you can see that as we go this way, we're getting smaller. And so that's what drove the development of these kinds of algorithms. So the original development was Radix-2. Then came this more generalized viewpoint with other radices. And then people came up with the split radix idea, and there are some other methods that we don't even fit into this framework. There's the Winograd FFT algorithm, which is not really widely used, but has some advantages in some applications. So if you're really trying to fit things in with the minimum amount of computation, you can find some other methods that will minimize computation. I have to admit I don't really know what the ramifications are, but I'm guessing in these kinds of things you never get anything for free. So my guess is that as you go from Radix-2 to split Radix, there's going to be something that you're paying for. It might be more memory locations. It might be more complicated indexing schemes. So all of those things have to be taken into account. If you've reduced the number of computations, but your indexing schemes are so complicated that it slows you down, you may not be that far ahead. So figuring out the exact right way to do this, the best way, is no easy task. So I leave that to the people who know how to do it, and I deal with the algorithm side of things. Some other issues that that we've already talked about is this idea of in-place computation. So for a endpoint complex DFT, we only need 2n memory locations. 2n because it's complex, so we have to store a real part and an imaginary part. But as we've said, the in-place computation requires the bit reversal, so our indexing and control operations are quite a bit more complicated, and so that could be a disadvantage in some applications. So if you've got memory, you can double the memory up to 4n locations, and so now you've got an extra memory array that you can use for intermediate results, and it reduces the complexity of your indexing and control. You don't need bit reversal, but you need double the memory. So, but today memory is cheap and memory is small, so that might not be a big issue. And then figuring out when you're actually implementing this, and you're implementing it with FPGAs or multiple DSP processors, how can you parallelize this? How do you do trade-offs between some hardware versus software? There's the whole fixed point versus floating point. A lot of stuff to take into account. And like I said, companies that sell FPGAs and sell DSP chips. They have people on their staff who are working out all these things, and they will provide to you the software necessary, or well, FPGAs are kind of hardware, but they're kind of software. So they'll provide to you the resources to properly decide and implement these things. And then a final thing, we've been talking about the FFT to compute the DFT. How come we haven't been talking about the IFFT to compute the IDFT, to invert everything? Well, because we don't need it. Once you have the FFT, you can use it cleverly to actually implement the inverse DFT. So if we look, here is the equation for the DFT, and if we end up rewriting it here, we can take a complex conjugate. Sorry, this is the inverse DFT. And you'll notice that the main distinction between the DFT and the IDFT is a plus j and a minus j, and there's the 1 over n. So we can rewrite this. Whoops, let me clear this off here. Do it this way. So we can rewrite this way. We put a complex conjugate around the whole shebang. Then we put a complex conjugate on just the DFT result. And so the effect of this complex conjugate will undo that. And the effect of this complex conjugate will convert that negative j back into the positive j. But what we've done in doing that is we've got ourselves a DFT because it's got the negative j. So if we want to do an inverse DFT, all we have to do is take the thing that we want to do an inverse DFT of, take its complex conjugate, take a DFT, conjugate that, divide by n, and we've got ourselves an inverse DFT. So we can do that with an FFT algorithm. So there is no need for an explicit IFFT, although you may find that there are algorithms labeled, like in MATLAB, I believe there's an IFFT. Inside that code, it just does this. There's not a new algorithm. Okay, so that's one nice little trick to keep in mind. Let's go to the next page, and here's 2 tricks that we can play with to see how things work. So the first trick works like this. And we alluded to this when we talked about using the DFT to implement the overlap and save. So we said we could take 2 blocks of data, 2 successive blocks of data, and stick them into a single FFT computation and get that effectively for free. So here's the idea. So suppose I've got x1 of n and x2 of n, both real valued signals, both length n, and I'd like to have the DFT of x1 and the DFT of x2. So here's the trick. You shove x1 into the real part. You shove x2 in as an imaginary part of some new signal that we'll just call x. Okay, so keep that in mind, but let's think about if I had x, how would I get x1 and x2 back? Because that's the key to understanding how this works. Well, if I took x and added the complex conjugate to it, so remember the complex conjugate is x1 minus j x2. So when I add the complex conjugate, the imaginary parts cancel. I'm going to get x1 plus x1. That's why I divide by 2. Okay, so that's good. Got all that taken care of. Same thing to get x2 back, except now I'm going to subtract the conjugate. So now I have x1 minus x1, because the real part doesn't change. And then I have plus jx2 minus a minus jx2. So I end up with 2jx2. I divide by 2j, and I get back x2. So given that idea, we can say, well, I can get the DFT of this by taking the DFT of this side, pass the DFT around each of those, and so I can get the x1 of k, the DFT of x1, by taking the DFT of my x and taking DFT of x conjugate, adding those two things together and dividing by 2. Same thing over here. I can get the DFT of x2 by taking the DFT of x, DFT of x conjugate, subtracting them and dividing by 2j. Okay? Still, though, looks like we have to do two different DFTs. DFT of x and DFT of x conjugate. But hey, remember all those properties we went through for DFTs? There's a reason that we go through those, because those things help us figure out tricks. And here's one time when we can use one of those DFT tricks. So it's easy to show, and I think we probably discussed this before, that the DFT of x star is really just the conjugate of the DFT indexed backwards. Okay, great. So I take my DFT of x, that's one DFT computation, done with an FFT algorithm. I then conjugate that. That's easy because that's just flipping a sign bit on the imaginary part, so that's hardly any cost at all. And then I just have to take the DFT and add it to the conjugated DFT indexed backwards, and then divide by 2, and I get my original DFT. I can do the same kind of thing to get back x2. So this is something that you can try in MATLAB using the FFT command and literally doing this indexing backwards and so forth. Try it with a size 8 FFT just to see how it works. So you can explore that and see that it does indeed work. Okay, so one other little trick here. That was using two different signals. Here we've got 2n points, and I want a full 2n point DFT, but it's a real valued signal. So let's let G be a real valued signal of length 2n, and I want a 2n point DFT of that. And so here's what we're going to do. Here's a little trick. We'll define x1 to be the even indexed elements, and we'll define x2 to be the odd indexed elements of G. And then we'll shove each one of those into a new signal x. So the even elements go in as the real part, the odd elements go in as the imaginary part. All right, that's good so far. Now, this is setting us up for doing effectively the same kind of thing as trick number 1. So trick number 1 tells me that I can get the DFT of x1 just by doing this trick. And I can get the DFT of x2 by doing this trick. Okay, so now I've got, remember this is an n point DFT, this is an n point DFT, but they are evens and odds. And remember, when we developed our decimation in time FFT, we saw how to combine an n over 2 point DFT of the evens with an n over 2 point DFT of the odds to get a n point DFT of the whole thing. So we can do exactly the same thing, and that's what we're doing here. And then just rewriting it in terms of the x1 and the x2. And then this is our final result. So we can end up getting g of k. We do this trick to get the x1, which goes in there. We do this trick to get the x2 that goes in there, and we evaluate that for k equal 0 to n minus 1. We now take the same things that go in here, but now they get hit with a negative of that twiddle factor, and we compute those numbers, again, for k equals 0 to n minus 1, but they get put into the upper half of G. And so this is also something you can check out on MATLAB. Lost my brain there for a minute. So that's all we've got for this set of notes, and in fact this finishes our study of the DFT. You should now be armed with all the tools necessary to do lots of MATLAB-based processing with DFTs and FFT algorithms, and we'll be moving on next into design of filters. We'll talk about FIR filters first, and then we'll move into the design of IIR filters. So we'll see you in the next set of notes.